So here we're going to do division of complex numbers, and let me show you what you can do. First of all, if you have just a whole number over just a pure imaginary number like this, 2 over 5i, you could use the conjugate, which is minus 5i, but really you don't have to, because if you just multiply the 5i down here by I, that will actually eliminate the complex number from the denominator. And so that's actually what we're doing. We're actually rationalizing the denominator so that we get rid of the complex number. So since I only have to multiply the denominator by I to get rid of the complex number, I also would have to multiply the numerator by I. So in the numerator I'd have 2i, and in the denominator I'd have 5i squared. And remember, I squared, is negative 1. So I have 5 times negative 1, which is negative 5, not 25. That's my bad. So that should be negative 5. I guess that's my bad. I guess I squared the 5 by accident, but that's actually, you don't square the 5, you just square the I squared. So that should be negative 5. And so now the final answer, if I go ahead and put the negative out here, then I get negative 2i over 5. So negative 2i over 5, or you could just say that's negative 2/5 I. If you wanted to write it like that, you could write it like that. Okay. Alright, so the next one here, it's when your denominator contains a true complex number in the form of a minus bi or a plus bi. Now here it's in the form of a minus bi. So if my denominator has a minus bi, then I must multiply by a plus bi. So in this case, since that's 2 minus 5i, I'm going to multiply 2 minus 5i times 2 plus 5i in the denominator, and I also have to do that in the numerator. Okay, so multiplying the denominator, that's actually the easy part, because since this is 2 minus 5i and this is 2 plus 5i, I can use my difference of squares formula, and I'll just get 2 squared, which is 4, and then minus 5i quantity squared. So here we square the 5. So I get 4 minus 25i squared. Alright, now in the numerator I have to FOIL. So I would do 3 times 2 and get 6. Then I'd do 3 times 5i and get 15i. Then I'd get 4i times 2, which is 8i. And then I get 4i times 5i, which is 20i squared. Now the next thing I need to do is I need to remember that everywhere there's an I squared, I can actually replace that with negative 1. So right there I can replace that with negative 1, and then that will make that a minus 20. And also right here I can replace the I squared here with negative 1. And when you take negative 25 times negative 1, you get plus 25. So I put a plus 25 here. Now, since this is 6 plus 23i minus 20, I can do 6. I can combine 6 and minus 20 and get minus 14, because 6 minus 20 is minus 14. And then the 15i plus the 8i combined is 23i. So I have minus 14 plus 23i. All over 29, because 4 plus 25 is 29. Now, some instructors like you to break this up into the two portions, where you have the real portion, which would be the negative 14 over 29, and then the imaginary portion, which would be the plus 23 over 29 times I. And then that way it's in the form of a plus bi. In this case, a would be the negative 14 over 29, and the b would be the 23 over 29. And so that's your final answer there. Now I decided to go ahead and do one that was in radical form. So just remember, the first thing you should do is simplify your radicals before we do anything. So square root of 2 and square root of 5, I can't do anything with that. But square root of negative 7 I can write as I times the square root of 7. So now here I have a minus bi, because I have square root of 5 minus square root of 7 times I. So that's like a minus bi. So to eliminate the I from the denominator, I've got to multiply by the conjugate, which would basically be the same thing except the sign would be opposite. So since this is square root of 5 minus I squared root of 7, I'm going to multiply it by square root of 5 plus I squared root of 7. And I also have to multiply the numerator by that as well. So now on the denominator, again, since I've got like, a minus b times a plus b, I can write this, do difference of squares, and say it's square root of 5 squared is 5, and then minus the square root of I times square root of 7 squared. Well, the I squared is just, the I squared is I squared, and when you square the square root of 7, you get 7. So I end up with 5 minus 7i quantity squared. And I'll go ahead and write that for you. Give me just a second here and I'll write that for you so you can see it better. Okay, so forgive my my writing here, but it's kind of hard sometimes to write these out using the mouse. But if you take square root of 5 minus I square root of 7 times square root of 5 plus I square root of 7, and you apply the difference of squares formula, that would just mean you square the first term. So we square the square root of 5, and then minus I square root of 7 is quantity squared. So you'd square the I square root of 7. Well, if you square the square root of 5, you get 5. And if you square the I square root of 7, if you square I, you get I squared. And if you square the square root of 7, you get 7. So I just wrote this up here. Instead of 5 minus I squared times 7, I wrote it as 5 minus 7 times I squared. And so that's how I got that denominator. Now, as far as the numerator, I just distributed the square root of 2. Square root of 2 times square root of 5 is square root of 10. And then square root of 2 times I square root of 7. Well, since square root of 2 times square root of 7 is square root of 14, that's going to be I times square root of 14. Okay, now back to the denominator here. Remember that I squared is actually negative 1. So I actually have here minus 7 times negative 1, so that's going to be plus 7. So I'm going to have 5 plus 7, and that's where the 12 here comes from. Okay, so now I have square root of 10 plus I square root of 14 in the numerator, and I have 12 in the denominator. And remember a minute ago I told you that sometimes you're required to break this up into two parts. So the real part here would be the square root of 10 over 12, and then the coefficient of the imaginary part would be square root of 14 over 12, and then you're multiplying that by I. So actually you could write the I there, or you could actually write the I out here beside it. So either way, it doesn't really matter there, but you could put the I with the square root of 14 or out beside the entire fraction. Okay, so that is basically what you're doing when you're dividing fractions that involve complex numbers. Okay, so that's basically the division of complex numbers. Now I wanted to finish it up here with equations involving complex numbers, and you'll see some of these in the section on quadratic equations. But if you wanted to solve x squared equal negative 64, then you would apply the square root theorem and you would get x equal plus or minus the square root of negative 64. And the square root of negative 64 is 8i, so x would equal plus or minus 8i. Here's another one. If you wanted to solve x minus 5 quantity squared equals negative 9, you could apply the square root theorem and you get x minus 5 by itself equals plus or minus the square root of negative 9. And actually, I skipped a step there, but if you replace the square root of negative 9, remember the square root of negative 9 is 3i. So that's the same as saying x minus 5 equals plus or minus 3i. And then if you add 5 to both sides, you get x equals 5 plus or minus 3i. And here's another one that I thought was interesting. X to the fourth is 81. So apply the square root theorem, and that would tell us that x squared has to be plus or minus the square root of 81, which is, let me write that out again for you. So that would equal plus or minus 9. If I can get it to write for me. All right. So x squared equals plus or minus 9. Now, so that means x squared equals 9. Now, if x squared equals 9, then we know we can apply the square root theorem to that and get x equals plus or minus 3. But the other equation that I would have would be x squared equals negative 9. And so if I have x squared equals negative 9, then x would equal plus or minus the square root of negative 9, and the square root of negative 9 is 3i. So this equation has 4 solutions: positive 3, minus 3, positive 3i, and minus 3i. Now I wanted to end on this. Some instructors like to talk about powers of I. Well, it turns out that I to the first is just I, but when we know that I squared is negative 1, well, I cubed, sorry about that, got something on the stove here going, so I had a timer set. So anyway, so I cubed would be I squared times I, and since I squared is negative 1, then you'd have negative 1 times I, which is negative I. So I cubed will equal negative I. And then to get I to the fourth, you could simply square I squared. But if you square I squared, that's the same as squaring negative 1. So I to the fourth would be 1. And then it just rolls over. So again, then I to the fifth would be I to the sixth would be negative 1, I to the seventh would be negative I, and I to the eighth would be 1. So it turns out that every fourth power of I is always going to equal 1. So that helps us to solve for larger powers of I. So for instance, if I wanted I to the 44th, if I wanted to figure out what that equals, well, I could say, well, I to the 44th is the same as I to the 4th raised to the 11th power. And since we know that I to the 4th is positive 1, that would be positive 1 to the 11th power, and 1 to the 11th power would be 1. Or if you had like I to the 47th, you could write that as I to the 44th times I cubed. And since we just learned that I to the 44th is 1, and we know from up here I cubed is negative I, then the final answer would be 1 times negative I, which is simply negative I. So anyway, I don't know if you'll have to run into those examples, but they're usually stuck in the book in the homework anytime you have problems that involve complex numbers. All right, so that basically completes the lecture on complex numbers. And again, remember, if your course doesn't include any lectures on complex numbers, then this is truly optional for you.